Welcome to the course VLSI Physical Design Automation. In today's session, we are going to discuss Prim's algorithm and the Kruskal's algorithm. In the last session, we remember that we discussed about what do you mean by spanning tree and what is the relationship between the spanning tree and the graph. And also we have seen that once we have having a graph, how to form a spanning tree and what are the different possible combination of spanning trees possible by means of a mathematical formulae. And also we are trying to understand what will happen if I am going to form a different possibility of spanning tree when a graph is given with a weight. And we noticed that the cost is going to play a vital role when we have a different combination of spanning trees possible for a given graph. So means for every possible combination of spanning tree, the cost of the spanning tree is getting different. So in today's session, we are going to see a specific search algorithms like Prim's and Kruskal's, where we can able to follow some procedures to see that how to form a minimum spanning tree. We used to call in short form is MST, a minimum spanning tree, minimum spanning tree. How to form a minimum spanning tree with low cost of a given graph. So that is the objective of this Prim's as well as Kruskal algorithm, and let me see one by one how the problem can be get solved for the Prim's algorithm and how the problem can be get solved by using the Kruskal algorithm. Okay. So as per the introduction, here the Prim's algorithm is one of the greedy search algorithm. All of us, we really well aware what is the meaning of greedy search algorithm. Greedy search algorithm is one type of search based algorithm. We have already seen that in many times, and this is going to be work based on the local optima. The greedy search algorithm is going to be work based on the local optima. So the main output of this Prim's algorithm is nothing but forming a spanning tree ST, and it should have a minimum cost of a given graph G. At the same time, we must make sure that we are visiting all the vertices available in the graph, and also we have to see that it has to satisfy your E dash is nothing but capital V minus 1 as the number of edges has to be present in our formation of spanning tree. So for that, the Prim's algorithm, a person who given a procedure how to do so to form the minimum spanning tree. Let me take an example of graph 1. Here let's say for example 6 with the weight of 10. Here I have taken example of 2, second node with the weight of 28, and here we have 5 with the weight of 25, and here I have the weight of 7, and let I assume that this is 24. Then here 2, we can assume that this is 14. Then we assume that here I have a 4, so this is 22, and I have assumed that this is nothing but 18, 2 to 4. Then here there is one more node is 3, from 2 to 3 is 16. Then from there we can able to form that is nothing but 12. This is the given graph. This is what the graph is given. Now our job is to form a spanning tree. What spanning tree? Minimum spanning tree. By using what algorithm? By using Prim's algorithm. So what Prim says? The Prim says that once the graph is given, you see that how many number of vertices and how many number of edges is possible, you identify it. So V dash is nothing but mod of V, that is nothing but how many vertices are available here? 7 vertices are available, so that 7 vertices will come over here. And see that what is the E dash is possible, we can say that mod of V minus 1, 7 minus 1, so there should be possibility of how many edges? 6 edges going to be get possible when you are going to form the output of your Prim's algorithm spanning tree. Now what Prim says that you always start with the vertices which holding the least weight from the given graph. Okay, that is your initial seed step we have to follow in a Prim's algorithm. Okay, what he says, we have to start with the least we have to start with the vertices which holding the least weight among the given graph. Okay, so likewise in step 1 we can start with this, what is this least weight is going to be getting holding. Accordingly here the least weight is nothing but 10, so we start with the vertices your 1 as well as 6, rather the remaining weights are 28, 14, 24, 25, 22, 18, 12 and 16. So 10 is going to be the least weight. So what we can do, I will just start with the least one. So I am just starting with 1 to 6 I am going to form, that is the weight is nothing but 10. Okay. So now the Prim says that once you made a seed vertices, okay, once you made the seed vertices, now from the seed vertices what is it available, you see that what is the minimum nearby vertices or the adjacent vertices we can visit which can hold the least weight. And also he is very particularly saying that don't further far away, don't select any kind of edges which holding the least weight, that might be leads to which may not forming the spanning tree. So he is saying that, see that from the existing vertices, means what is it existing vertices, already we have selected 1 and 6. Why? Because the 1 and 6 holding the least weight, that is nothing but 10. So from these least vertices which you have selected, you see that what is the other possible minimum we can able to visit. So in that case we can check the adjacency. Okay, I will just redraw this here, I will redraw this here. So this is okay, right, so this is 1, right, this is 1 and this is 6 and this weight is 10, correct. So here the possibility is nothing but 1, either 1 I have to, from 1 I have to look for it to go for with next minimum, or from 6 we have to look for it to go for next minimum. So from 1 I am looking for what is adjacency, that is nothing but from 1 we can go to 2, but the weight is 28. But what is the next possibility? From 6 I can go for next adjacency to cross verify, that is nothing but 5, which having 25. When comparing 28, 25 is minimum, so I can go from 6 to 5, so I can go to 6 to 5, that is nothing but 22. According to the Prims, from the seed nodes, see that what adjacency we can visit, at the same time that particular adjacency node should have a least weight. Accordingly we have going from 6 to 5 rather to go from 1 to 2. Now what is the nodes are available to check the adjacency? Again the one can be get explored, because 1 to 2 is neighbor adjacency is available, the weight is 28, and from 5 we can able to go to 4 or we can go to 7. So if we go to 5 we can go to 4 means it is 22, okay, and if I go from 5 to 7 means it is 24, and from 1 if I go to 2 means that is 28. So among which we can see that the 5 to 4 visiting is having the least weight, that is nothing but 22. So we can able to go for 5 to 4. Okay. Now what else is possible? I can check the possibility to visit from 1 because still 1 is open, and I can check the possibility to visit 5. From 5 I can able to check the neighbors, and from 4 we can able to check the neighbors. Okay. So now from 1 we can visit 2, that is 28 is the weight, and from 5 we can visit 4, that is 24 is the weight, and from 4 there is a visit to go to 3, that is nothing but 12 in a weight, because 5 to 4 is already visited. So that now we can able to cross check 1, 5, 4, among which your 4 to 3 is going to be the least weight, so I am visiting 4 to 3, that is nothing but 12. Okay, that is visited. Now what else we can able to explore now? We can explore the possibility of visiting from 5 once again, because 5 to 7 connectivity is existing now still. From 1 to 2 is 28, it's very higher. 5 to 7 is 24, it also seems higher, and 4 to 7 is 18, seems higher, and 3 to 2 is going to be 16, it seems better. Why? Because it is going to be the least weight, so I am going to visit is nothing but 16, your 3 to 2. So 3 to 2 is nothing but 16, so 3 to 2 I can go to 16, right. So now what is the possibility? We can go for possibility what 1 to 2 is possible, but the Prim is also saying that another one additional procedure or a constraint, if you are going to choose, even though the particular edge is going to become least weight, if that particular get forms least or even though that particular edge is least weight or the highest weight, even if it is going to be selecting because of it, if we are going to form any kind of closed loop, then we should not select that particular edge. So if we are going to select this particular 1 to 2, because 1 to 2 still we can check the neighboring, right. 1 to 2 is 28, it is very higher, but if we are going to close this 1 to 2, it will become a, it will form a path, it will form a loop, so we should not select it, we are leaving it. And 5 to 7 is possible, that is 24. If I go to 5 to 7 is 24, means it is very higher, and 4 to 7 is possible, it is going to become 18, is also very higher, and 2 to 7 is possible, that is nothing but 14, that is the least weight, so we can go for 2 to 7. So 2 to 7 is nothing but 14, we can say that. Now say that now 5 to 7 we can close it because it will form a loop, and 5 to 4 we can close, 7 to 4 we can close it, it will also form a loop, and 1 to 2 we can close it and it also form a loop. So there is no other further movement by using the Prim's algorithm. So we can see that we have visited all the nodes. Now you check how many number of nodes are available, and there is 7 vertices are available. Yes, of course the condition is satisfied, and we are checking out the spanning tree. The spanning tree must consist of only 6 edges. At the same time it should not contain any kind of closed path. Yes, of course there is no closed path on the spanning tree which we have formed over here, and number of edges must be 6. So we can check the number of edges, how many number of edges available. So we can see that your first edge number 1 and 2 and 3, 4, 5, 6, of course we have 6 edges going to be getting available. Now what Prim's claims that accordingly whatever the combination you are going to apply hereafter, that any combinations will not going to provide you the minimum cost than the spanning tree which is formed now. And that is what, now what is the minimum spanning tree cost? Cost of minimum spanning tree is nothing but addition of or sum of all your edge weights. So how we can able to do so? It's nothing but 10 plus 22 plus 22 plus, oh not 22, this is 25, right, this is 25, okay. So 10 plus 25 plus 22 plus 12 plus 16 plus 14 will be your a total thing. So we can say that the cost can be is equal to 99. That is what it says, and this is the procedure it's going to be get followed by the Prim's algorithm. So how the Prim's algorithm started, the seed vertices can be selected from the given graph is nothing but the vertices which holding the least weight of among your given all edges. Accordingly, we have selected, after forming the seed vertices, we have to see that what neighboring vertices we can visit which holding the least weight from your seed vertices. Accordingly, we can move on and to see that whenever it is forming the loop, even it holding the least weight of edges, we should not make use of the loop to form. Why? Because our objective is to forming the spanning tree, and this is what the way the Kruskal algorithm gets solved. Sorry, this is what the way the Prim's algorithm is get solved. I am sorry for that. Now let me move on. After that, Prim's is get identified this particular procedures to solve. In later, the Kruskal is coming to the picture, and he just given that a different alternative procedures to form the same spanning tree, minimum spanning tree with the least cost. Here the wonder is, whatever the so-called minimum cost identified by the Prims will be is equal to the cost which is identified. The Kruskal is going to be same. And let's see that find by the procedure. What is the procedures to follow the Kruskal algorithm? Okay. So accordingly, the Kruskal's algorithm, what we can do, we can able to take the same problem for solving it. So what is the problem we have drawn in the previous case? We have 1, here 6, this must be 10, here is 5, 25, here is 4, this is 22, here is 2, this is 28, and this is going to be 7, and this is 24, and this is 14. Here I have 3, that is nothing but 12, and here we have 16, and this we have 18. This is what the previous graph we have taken for the Prim's algorithm. We can select the same graph for your to understand your Kruskal's algorithm too. So how it is going to be getting forming. So what Kruskal says, that he saying that you just arrange all your weights in a ascending order. All the weights in the ascending orders, he says. Means he just asks you to arrange from your lower weight edges to the higher weight edges. Means you form a table through which you just write it down. What is the lowest weight and what is the nodes between that lowest weight? That's what he asks you to form a table. Once you form a table, you just start to follow and form the edges which is holding the least weight and its respective vertices as a outcome of your graph to form a minimum spanning tree. In this procedure, if any minimum spanning tree is going to be getting forming, and if it is get formed, due to which if it is forming any kind of a loop or the path, we should not choose even though the weight is going to be lower. That is what the Kruskal says that. Accordingly, how we can able to solve the problem of Kruskal? So what Kruskal says that you select which is holding the very least. Means what is the least is nothing but 10 is the least one. So we can say that let me take the same color over here. So 10 is the least one. So 1, 2, 6 is nothing but 10. Of course, Prim's also selected the same. But once the Prim's is selected this one, and what after that what he said is nothing but like whatever the so-called seed vertices are available, from there only you look for the neighbor. That is what the Prim statement. But Kruskal says that no need to worry about the existing seed vertices which you already taken, and see that is there any other minimum possibility of vertices are available in a graph. You take it that also further to form a tree, so that it will form a spanning tree. At the same time, in this procedure, if you found that any kind of edges is forming a loop or the path, you avoid it. Accordingly, we can choose what is the next least weight is nothing but 12 between 3 to 4. So we can choose 4 to 3 is nothing but 12 in your step 2. Then what is the least weight? We can say the least weight is after thing is nothing but 2 to 7. So we can choose 7 and we can choose 2, that is nothing but 14. This is what next one we can able to form. right? Now what is the next least weight we can able to get formed? That is nothing but is 16, because 10 is over, 12 is over, 14 is over, next is nothing but 16, that is 2 to 3. So we can say 2 to 3 is 16, we can select that one. Then what is the next least weight? That is nothing but 18. If I am going to choose 18, this 18, if I am going to form 18 here like this, what will happen? It is forming a loop, because this is a loop. So 2, 3 is 4, 8 is 2, 3, 4, 7 is a loop. So Kruskal says that even though it is a least weight is going to be getting existing, because of which if there is any loop is getting forming, we should not choose that one for our selection. So we are not going to choose this one, we are going to avoid this 18. So what is it? What else is going to be available least more than this 18? So it means next is nothing but what, 22. So that is nothing but 4 to 5. So I am going to 4 to 5 is nothing but 22. Then what else we can able to move on? We can able to move on from 22 to what, 24. So what will happen if you are going to choose this 24? If you are going to form this one, it's become, if this is going to 24, right? If this become loop, because it's going to become 2, 3, 4, 5, 7 is going to become loop. So we should not select this actually, so that we are going to avoid this next minimum. So what is going to be available compared with 25 and 25? This is minimum, 25 is minimum. So we can choose 6 to 5, that is nothing but 25. So according to the minimum spanning tree, we know that V dash is nothing but V, that is equal to here also 7, and E dash is nothing but V minus 1, that is nothing but 7 minus 1 is equal to 6. Yes, of course it is satisfied. So this is what the difference what we can able to see between your Kruskal's algorithm as well as your Prim's algorithm, right? So what is it says that the what will be your now time complexity, big theta is going to be is nothing but, like we can say, we have to check with all vertices will be available for your spanning tree, and here we must have E dash. So we can say V dash and E dash will be the spanning tree, and in this case is nothing but your V, and E this is nothing but your V minus 1, we can say is it's nothing but 2V, it's going to be minus V, right? So we can see that like this can be get cancelled, sorry, this is going to be not 2V, this is going to be V square minus V. So this will be get cancelled. So big theta is nothing but V square, which represents that big theta of n square will be the time complexity to explore your Kruskal's algorithm to form a spanning tree. And if you here also, if you are going to calculate your cost of the minimum spanning tree, cost of minimum spanning tree is equal to 99 will be going to form, because the same thing is getting formed. And these are the different two procedures we are following to form this minimum spanning tree without spending the all combination of possibility to explore. At the same time, we just see that we can able to produce the minimum cost for our exploration of all the nodes, right? And next class, let we discuss about a different algorithm, Dijkstra algorithm, where we can able to understand how we can able to visit specific nodes between the source and destination with the minimum cost. That is what is explored by the Dijkstra algorithm, right? Thank you so much.